RLC series combinations. Now let's put a resistor, capacitor, and inductor in series. At any given time, the voltage across the three components in series, V series, T, is the sum of these. V series, T, equals VR, T, plus VL, T, plus VC, T. The current I, T, we shall keep sinusoidal, as before. The voltage across the resistor, VR, T, is in phase with the current. That across the inductor, VL, T, is 90 degrees ahead, and that across the capacitor, VC, T, is 90 degrees behind. Once again, the time-dependent voltages V, T, add up at any time, but the RMS voltages V do not simply add up. Once again, they can be added by phasors representing the three sinusoidal voltages. Again, let's freeze it in time for the purposes of the addition, which we do in the graphic below. Once more, be careful to distinguish V and V. Look at the phasor diagram. The voltage across the ideal inductor is anti-parallel to that of the capacitor, so the total reactive voltage, the voltage which is 90 degrees ahead of the current, is VL, VC, so Pythagoras now gives us V2 series equals V2R plus, VL, VC, 2. Now VR equals IR, VL equals IXL equals IL, and VC equals IXC equals I/omega C. Substituting and taking the common factor I gives. Where series is the series impedance, the ratio of the voltage to current in an RLC series circuit. Note that, once again, reactances and resistances add according to Pythagoras law. Series 2 equals R2 plus total 2. Equals R2 plus, XL, XC, 2. Remember that the inductive and capacitive phasors are 180 degrees out of phase, so their reactances tend to cancel. Now let's look at the relative phase. The angle by which the voltage leads the current is phi equals tan 1, VL, VC, slash VR. Substituting VR equals IR, VL equals IXL equals IL, and VC equals IXC equals I/omega C gives. The dependence of series and phi on the angular frequency omega is shown in the next figure. The angular frequency omega is given in terms of a particular value omega, the resonant frequency, omega 2 equals 1/LC, which we meet below. Setting the inductance term to 0 gives back the equations we had above for RC circuits, though note that phase is negative, meaning, as we saw above, that voltage lags the current. Similarly, removing the capacitance terms gives the expressions that apply to RL circuits. The next graph shows us the special case where the frequency is such that VL equals VC. Because VL, T, and VC are 180 degrees out of phase, this means that VL, T, equals VC, T, so the two reactive voltages cancel out, and the series voltage is just equal to that across the resistor,